Princeton Adult School's Science Times, Exploring the Frontiers of Science. I'm Dr. Mark Brannon, and I'm the president of the Princeton Adult School. It's really a pleasure to see all of you here in spite of the beautiful spring-like or summer-like weather that we have outside tonight. One short announcement before we go into tonight's lecture, and that is regarding the last lecture. We only have one more in this series, and that'll be next Tuesday night. And at that time, we hope to be able to announce the topic and speakers of the upcoming semester's lecture series. I can tell you that the committee has been working furiously to try to get all of these together this week. There's been a lot of work on it, and I hope that everything will be in place so we can make our announcement and maybe even have a handout to you if you come next week to whet your appetite for yet another wonderful semester of classes. Okay, on to the business of this evening. It's really a pleasure for me to be able to introduce Stuart C. Prager as tonight's speaker. Professor Prager is the director of the Princeton Plasma Physics Laboratory, and he's also professor of astrophysical sciences here at the university. He is the sixth director of this center, and it is a Department of Energy National Science Laboratory. There's only 10 in the country, and this is one of them. He, as mentioned, has been the professor of astrophysics here at Princeton University since 2009. He received his bachelor's from both the Queens College of the City University of New York and Columbia, and then received his PhD in plasma physics from Columbia University in 1975. Following 2 years performing fusion energy research at General Atomics in San Diego, he joined the University of Wisconsin at Madison, Wisconsin, as an assistant professor at that time of physics. He remained at the University of Wisconsin as the Dexter Professor of Physics until 2009, when he came to Princeton to assume his current position. Professor Prager's research interests are on basic plasma physics, particularly applications of fusion energy, and more recently applications to astrophysics. While at Wisconsin, he was director of the Madison Symmetric Torus Experimental Facility, supported by the Department of Energy. He also served as director of the Center of Magnetic Self-Organization in Laboratory and Astrophysical Plasmas, established through the National Science Foundation's Program of Physics Frontier Centers. Professor Prager has participated in numerous scientific planning and advisory processes, including services as the chair of the Department of Energy's Fusion Energy Sciences Advisory Committee. He also served as chair of the Division of Plasma Physics of the American Physical Society and as president of the University Fusion Association. He was a co-recipient of the American Physical Society's Dawson Prize for Excellence in Plasma Physics. And he's had many other awards, which are too long to get into tonight, but it is, without any further delay, the topic that he's chosen to talk about tonight is the path to fusion energy, from physics to energy, and please help welcoming Professor Stuart Prager.
Well, thank you for that very nice introduction. Can you all hear me okay in the back? Okay, great. Well, thank you for coming out tonight, and I'm very happy to be able to tell you the story of fusion energy. And it's a story that's still being written. So this is, fusion energy is one of the biggest physics and engineering challenges ever undertaken. But on the other hand, the payoff will be one of the biggest payoffs that you can get from applying science to societal problems. So I'm going to describe to you today what fusion is, why it's interesting, what the scientific challenges are, how far we've come, and a little bit where we have to go. A good way to start is with the sun. It all starts with the sun. This is a picture of the sun, and the sun is what we call a plasma. And a plasma is just a gas of electrically charged particles. So the air in this room is a gas of neutral molecules. They're not electrically charged. And a plasma is nothing more than a gas where the particles are electrically charged. And let me say at the outset, it's not blood plasma. Okay, that's completely different than that. So the sun is a plasma. And if you want to understand how the sun behaves, you have to understand how plasma behaves. And not only is the sun a plasma, but all the stars are plasmas, and most of the universe that we can see is made up of plasma. So one can give a whole talk about the plasma universe that's out there, but that's not my topic for today. The topic for today is using the source of energy that's generated in the sun, using that here on Earth. And the sun generates all of its energy by nuclear fusion reactions, which I'll describe in a few moments. That's why the sun gets hot and generates its heat. It's because nuclei are fusing together and in so doing generate energy. This was realized in the late 30s. Hans Bethe got a Nobel Prize for that realization. That was late 39, 40, 41. Early 50s around the world, scientists, particularly in the Soviet Union and the United States, realized, gee, this source of energy that drives all the stars can maybe be used here on Earth. At first it was classified. When it started in the early 50s, in 1958, there was a conference in Geneva where everybody just showed what they were working on. And ever since then, it's been a very open scientific exploration. So the sun generates its energy by fusion, and so it would just be swell if you can just take a sun, small sun, that's hot, put it in a box here on Earth, and let it generate the heat, and use that heat to make electricity. That would be a terrific solution. So why don't we just do that? And it's often said that the goal is to create a star here on Earth. And that metaphor, I think, is a pretty good one. That is really what we're trying to do. Well, this won't work. And why won't it work? Because the reason that the sun is held together in a nice sphere is because of its own gravity. It's so massive that it just hugs together, just like we're held to the Earth by gravity. The sun is just held together there by its own gravity. But it's impossible, practically impossible, for us to make a plasma here on Earth that is so massive and so dense that gravity would play any significant role whatsoever. So this doesn't work. And so, realizing this doesn't work, then what do you do? And thus begins the story. Now let me start, not yet with the plasma physics, but just talk about the fusion reaction itself, which is a problem in nuclear physics is completely solved. Two nuclei of the atom fuse together, and in so doing, some of their mass is converted to energy. So imagine you have two blue nuclei here, and you smash them together so that the two nuclei smash together and they fuse. When they fuse, they generate, there's a transformation, and they are converted to new particles that then fly apart. And so the net result is you have initially two nuclei, let's call them blue, and the nuclear fusion reaction gives rise to two different kinds of particles, let's call them red. And the nice thing is that the initial nuclei can be relatively slow-moving compared to the two nuclei that come out of the reaction that are relatively fast-moving. So there's a production of energy. You start with two relatively slow-moving nuclei. They fuse, and out come two fast-moving nuclei. Energy is produced, and how is energy produced? Well, it's the conversion of mass to energy. If you take the initial blue nuclei and you were to weigh them on a scale and compare with the weight or the mass of the two products, you'll find that the initial nuclei are heavier than the final particles. Mass has disappeared. And as I'm sure you know, that missing mass is converted to energy, to the kinetic energy of the moving products by Einstein's equation E = mc squared. That shows there's an equivalence between mass and energy. Mass is converted to energy. That is the nuclear fusion reaction. In a fusion reactor of the future, The particular nuclei that we'll use is the nucleus of the deuterium atom and the nucleus of the tritium atom. The details don't matter. These are forms of hydrogen. They're sometimes referred to as heavy hydrogen. They fuse together, form a compound nucleus that then splits apart into a helium nucleus and a neutral particle called a neutron. This is the fusion reaction that will be used. Now, to make fusion reactions is simple. The hydrogen bomb has done that. But the goal here is to do it in a controlled manner for peaceful purposes. The existing nuclear reactors don't operate on nuclear fusion. They operate on nuclear fission, where they're splitting the nuclei, and that so doing also converts mass to energy. So the current nuclear reactors are fission, splitting, and this one is fusion. Now, to put it a little bit schematically, what we do is a deuterium nucleus and a tritium nucleus combine together, and they give rise to a helium nucleus and a neutral particle, subatomic particle called a neutron. And if in some units of energy, these initial nuclei were moving, had an energy of unit 1, then these products would have an energy which is, order 1,000 times greater. So it's a very intensive, powerful source of energy. Now, you get this very large energy multiplication, much greater than you get from chemical reactions. The products are harmless. Helium you can use to blow up balloons, and neutrons just get absorbed in the surrounding structure of the reactor. They don't even escape. But you notice that the nuclei have positive electric charges. So you have two nuclei, each of which is positively electrically charged. You want to smash it together and get it to fuse. But as you push them closer together, the electrical repulsion makes it hard to do. So you have to get the particles moving very rapidly together so that they will fuse and overcome the electrical repulsion, and you get a nuclear fusion reaction. And what happens is the neutrons are absorbed by a surrounding blanket that gets hot, and then the heat of that blanket is converted to electricity by ordinary means. So for fusion energy to be practical, you can't just take two nuclei. That just doesn't generate much energy. You need billions and billions and billions of nuclei fusing at the same time. That's what happens in the sun. The sun has billions upon billions of nuclei, all of which are fusing with each other, and each fusion reaction generates a little bit of energy, and it adds up to a lot of energy. So we need many deuterium and tritium nuclei fusing together. They have to be moving very rapidly, the particles, to overcome the electrical repulsion. So we need a gas of very rapidly moving charged particles. When you have a gas of rapidly moving particles, it means the gas is very, very hot. How hot does it have to be? For a fusion reactor, it has to be about 100 million degrees. So we have to make a plus about 100 million degrees. For comparison, the sun is relatively cool. It's only 10 million degrees at the sun's core. So the goal is to make a little sun on Earth, but heat it up so that it's 10 times hotter than the temperature at the center of the sun, 100 million degrees. Another little factoid about the sun. In any cubic meter of the sun, so in a volume about this big in the sun, about 300 watts of fusion power is generated. And that's not very much, but the sun is so massive that it adds up to a lot. In a fusion reactor, we'll need to generate about 10 million watts in each cubic meter. So we have, I would say, a much more difficult challenge to make a fusion reactor than it was to make the sun. And it took billions of years to make the sun, so it won't take long. So it's a challenge. Now, why do we want to do this? Fusion energy is just about as ideal as you can get as an energy source. It's nearly inexhaustible. The deuterium comes from water, and there's enough water in the oceans to generate fusion for thousands upon thousands of years. About 1 out of every 3,000 water molecules is not H2O, but HDO. So about 1 out of every 6,000 atoms in the water of hydrogen atoms will be deuterium. And that's enough to generate for thousands of years. Tritium doesn't appear naturally, so tritium, this is a sort of a detail, is bred in the fusion reactor. Tritium is bred in the fusion reactor. So it's nearly inexhaustible, and when I got into the field in the 1970s, if you remember, I didn't know you do, there were long gas lines, we were running out of energy, and there was an energy crisis. And the limitless feature of fusion was one of the big attractions. Also, since the fuel comes from water mostly, it should be available to all nations. Hopefully it will reduce conflict over localized natural resources. It is just about perfectly clean. There is no greenhouse gas production, no CO2, no acid rain, no nothing. There is zero contribution to global climate change. Wasn't realized when I got into this field, but now this has become a reason for trying to achieve this second to none. And finally, it's extremely safe. There's no chance of any runaway reaction or meltdown or anything like that. And the reason is, a fusion reactor, you have to keep this plasma at 100 million degrees. And that's hard to do. Any malfunction and it will immediately cool down and the fusion reactions will quench. In addition, we keep injecting the fusion fuel into the plasma, and at any moment there's enough fuel in the reactor for it to generate energy only for a couple of minutes. Whereas in a fission power plant, you have these rods that are always there. So there's no chance of any catastrophic kind of accident. So it's nearly limitless, it's broadly available, it's perfectly clean, and it's highly safe. And that is what worldwide has driven this research program all the years, and the imperative for fusion only grows year by year. So this is why it's societally so exciting. Another way to illustrate a little bit its cleanliness is if you look at the daily fuel consumption and waste production from one power plant, and let's compare one coal-fired power plant at a gigawatt compared to a fusion plant generating the same energy. The fuel in each day to drive this coal plant is about 9,000 tons of coal. So you see these trainloads of coal being shipped into. Whereas for fusion, it's a few pounds of stuff is all you need for that same amount of energy. The waste produced in a coal plant is 30,000 tons of CO2, which is dumping waste into the atmosphere. One plant, one day. And in fusion, you get 4 pounds of harmless helium. And the fine print is the neutrons come out and they bombard the surrounding structure, and it becomes just mildly radioactive. So there's a mild radioactivity, but it's orders of magnitude less than in a current day nuclear power plant. So the goal here is really a fantastic goal. Unfortunately, as I said in the beginning, it's one of the most difficult science challenges you can undertake. That's the catch, is that it's difficult. The challenge is to produce and confine a hot plasma at 100 million degrees. It has to be dense enough that you get a lot of reactions going on. It has to be well insulated from its surroundings. I mean, you're going to have 100 million degrees at the center of this reactor, and then a few feet away, there's going to be a wall that's going to be close to room temperature. So you need some pretty good thermos to insulate it. And also, another reason it's more difficult than making the sun is because you have to surround this thing by a material chamber. The sun is out there in this vacuum in outer space, and you have to take the sun and you have to put a material wall around it. So you can imagine the materials challenges. So those are the challenges and the motivations. So how do we do it? How do we actually make and even hold together a 100 million degree plasma? In a magnetic force field. Can't use gravity, but there's another force, it's a magnetic force that you experience with magnets. And so here's a magnet making a magnetic force field. We all have experienced the force of a magnetic field. If you throw some particles into the into the magnetic field, here's a negatively charged electron and a positively charged nucleus. And if this arrow represents the direction of the magnetic field, that's the thing you make with the iron filings when you were in high school. The charged particles will spiral around the magnetic field like a train along a railroad track. So a magnetic field can apply forces on electrically charged particles. And that's the force that we use, but this won't work because if you have a plasma here, it's just going to be, the particles are just going to move horizontally and bombard the magnet and get lost, so it's not confinement. So what do? Well, instead of having this linear arrangement, you take the plasma and you bend it into a donut. So this is how it's done. You take a plasma, which in this cartoon is colored yellow, and you bend it into a donut, so you have no ends. You surround it by all these magnets, which are shown here in orange. So these are all magnets. And these magnets make a magnetic field inside the plasma that hold the plasma in a containment. They hold the plasma there. So you have this magnetic force field confining this donut-shaped plasma. A nice word for a donut is a torus. So you have a torus, a plasma in the shape of a donut or a torus or a toroidal plasma. One way to get it hot is to drive an electric current through it, the long way around. So we heat it by driving an electric current through the plasma. If you have current in your lamp wire and you drive too much current through it, the lamp wire gets hot, and that's not good. But here, we can drive an electrical current through this plasma, and the current heats up the plasma. The electrical energy of the current gets converted into the kinetic energy of the particles in the plasma, just like current flowing down a wire. In these plasmas, we flow millions of amps of current. So you drive millions of amps of current, and that heats the plasma to millions of degrees. This kind of configuration was roughly invented in the Soviet Union a long time ago, and it's referred to sometimes as a tokamak, which is a Russian acronym for toroidal magnetic confinement. You can also heat this up, just like you do a turkey in a microwave oven. You can inject electromagnetic waves into the plasma, and that can be used to heat it up just like a turkey in an oven. This is a cartoon of what a tokamak looks like, a little more realistically. There's a person, and you have a hot plasma there. The plasma is contained in a vacuum vessel that all the air is pumped out, and it's surrounded by these magnets. And to give you a sense of the state of the art, this is currently the largest operating tokamak in the world in England. And you can see that this is the chamber when it's not in operation. Here's a person. And when you do operate it, you eject the person. You pump all the air out of the chamber. You turn on the magnetic field, and then you introduce a plasma into the chamber. So this whole chamber is filled with plasma, 100 million degree plasma. And you can see that the walls are very heavily armored to withstand the intensive heat flux that comes from this 100 million degree plasma. So this is all armor to withstand the heat flux. These little panels here, you can't quite tell, but these panels are antennas that inject electromagnetic waves that travel around the donut and heat the plasma. And a fusion power plant, when you look from the outside in, will look very conventional. And so how a fusion power plant works, I alluded to it a little bit. You have this hot plasma here, this hot plasma furnace, like a flame, like a sun in there. But it's not generating its energy by chemical reactions like a fire in your fireplace. It's generating its energy by nuclear reactions. The neutrons come out from the fusion reaction. They get absorbed in a blanket that surrounds the plasma. The blanket heats up. It converts water to steam. That runs a turbine that then makes electricity. So it's completely conventional, except the core is not burning coal. It's not fission nuclear rods. The core is this hot 100 million degree plasma furnace, just like the sun. So I mentioned it's been a very big challenge, and what it's required has been the development of a new field of physics that was really accelerated by this fusion goal. And it's required the development of a new field of science called plasma physics to try to understand how plasmas behave, how this state of matter called plasmas behave. And that's come quite far over the last 40 years, 40, 50 years. And it's been accompanied by the development of a field you might call fusion engineering. And we've come very far. We now can routinely produce plasmas every day in laboratories across the world that are really at astronomical temperatures, where astronomical is not metaphorical. They're really at the temperatures that you find in stars and hotter. And so here is, this is real data from an experiment where the temperature is plotted versus the distance as you move through the donut. And you can see that the temperature reaches here, you can see it's cooler at the edge of the plasma. It's down to maybe 1 million degrees. But here it's at 300 million degree plasma that are made, 100 million degrees are made routinely. Not only can we make 100 million degree plasmas, but we can manipulate them with remarkable finesse. We learn how to control them. And you can control them by, as I say, injecting radio waves into the plasma. We can inject beams of particles that can heat the plasma. We can finely shape the magnetic field to control the plasma. Fusion energy has been produced in a laboratory. I mean, it's not just a figment of one's imagination. In fact, in 1994, in Princeton, for the first time ever, 10 million watts of fusion power was produced. And so here is the sort of historic piece of data. This is fusion power in megawatts, which is millions of watts. And you can see that this means that the plasma is heated. So this is heating is turned on, and fusion power is produced. It peaks at 10 million watts, and then as the plasma cools down, the fusion goes away. So for a fraction of a second, 10 million watts was produced. A rather historic experiment here in 1994. A few years later, in the United Kingdom, they went further and they produced 16 million watts of fusion power. At the time, this got a lot of headlines. Here are headlines that it got. It was very nice because it was a milestone. And these results triggered an increase in the fusion effort worldwide, everywhere, with an exception, and the exception was the United States. But the rest of the world then really accelerated their program, and it brought in new players, particularly China and South Korea, parts of Europe, and India as well. There's a, yeah, if you plot, unfortunately it's covered up. If you plot the fusion power produced versus year from 1970 up to the year 2000, you look behind these banners. We've gone from milliwatts in the 70s to these megawatts in the 90s in the year 2000. So there's been tremendous progress throughout the years. But if you plot it, you see it just gets better and better. It looks kind of like a featureless progression, like you're just working out for a marathon, running a little bit further distance each year. But really, this upward progress in the fusion power produced in the laboratory has been driven by new insights into plasma physics. So let me just give you a little bit of a taste of some of the challenges that have been met. And this is one example. To make fusion reactions, I had mentioned we want to get the plasma to be very hot, but we also want it to be fairly dense, because you need a lot of particles that are undergoing fusion. So to get a gas that's fairly dense, a lot of particles in it, and hot, means that you want a plasma that's at very high pressure. Pressure is density times temperature. But every plasma, you can't generate infinite pressure. Every plasma above a certain pressure is going to disassemble. Not in a dangerous way, but it's just going to sort of disassemble and blow up in a benign way. And over the years, we've learned how to increase and increase and increase the pressure in the plasma. And I'm just going to give you a little bit of a sense here of one recent advance. If you build a tokamak that has a very small hole in the center, so this orange stuff indicates the hot plasma, and this is a hole in the center. It's a very small hole. It's almost like an apple that's cored. And this gives rise to very high pressure. And just to give you a little glimpse of the physics behind it, on the right is plotted the magnetic field. So here you can see the donut. with a small hole in the center. And this black line indicates the direction of the magnetic field. And remember I said that a particle in the plasma will follow the magnetic field like a railroad car following a train on a track. Imagine you're a charged particle and you're moving around following this magnetic field line being contained by the magnetic force. When you're on the outside of the donut, the centrifugal force is going to push you out. When you get to the inside of the donut, the centrifugal force is going to push you in. And so having a tokamak that has a very small hole in the center accentuates this very good part of the plasma. And the inward force that confines the plasma is going to dominate over the outward centrifugal force that will throw particles out of the machine. So this strongly curved magnetic field has allowed us to get to very high values of the plasma pressure. And one reason I mention this is something that's studied out at the Princeton Plasma Physics Laboratory here. We have such an experiment with a small hole in the center, and this is what it looks like in real life with a lot of the equipment removed. Here's a person, and I just show it to say, would anytime invite anybody who wants to tour this to visit the laboratory. Another huge grand challenge in plasma physics and physics in general is to understand turbulence. You know that lots of items in nature tend to be turbulent. And turbulence, plasmas are sort of amazing things. If you just have a plasma and it sits there, it spontaneously starts to shake and wiggle and become quite turbulent. Unlike water in a bucket. It's as if you put water in a bucket and stand back and all of a sudden you see waves develop. This is what happens in these plasmas. They become turbulent. And when they become turbulent, the turbulence causes the plasma to cool down, and that's not good. When I started this field, we thought turbulence was inevitable, nothing you can do with it. It's such a hard physics problem, just like the weather, you have to accept it. But over the decades, physicists have learned how to control the turbulence. So here's a computer simulation, but this has been realized in experiments. And here you can see a plasma. The striations indicate turbulence that just take the heat, and the heat is ejected along these striations. But we've developed techniques that these big turbulent eddies are broken up, and when they're broken up, the plasma stays hot and the energy is contained. So we've actually learned how to understand and control turbulence in these plasmas. Another big challenge that we weren't really expecting is that these plasmas that kind of have a mind of their own every now and then disrupt. And so there's a big challenge in what we call disruptions. And these are like explosions in the plasma. And they don't endanger anything, but you can't have them in a reactor because they'll damage the reactor walls. And here's an example of a disruption in a plasma. Here's a piece of data plotted versus time just over a second in a particular plasma experiment. And here the plasma is carrying a current of 2 million amps, and in a fraction of a second it all goes away. And here's the plasma temperature, in this case at 10 million degrees, and in a fraction of a second the plasma cools down to 0. We don't want this to happen, but the plasma does this. And it's not a good thing. And why does it happen? Because the magnetic field spontaneously just breaks up and scrambles. And this isn't good because all the power is dumped onto the wall surrounding the plasma and it will damage the wall. It actually has physics similarities to this. This is a solar flare. Here's the sun, and this is a real observation. And every now and then, the sun is a very violent place. Every now and then, the sun generates this huge flare of plasma. And for scale, this is the size of the Earth. So this is called a solar flare. Let me just imagine it. And the sun just does it spontaneously. And this is another moment it'll just pop out of here, some other times pop out of there. You can see little arcs here. You can see how turbulent the sun is. This is occurring because there's a magnetic field on the surface of the sun, just like there's a magnetic field surrounding the Earth. And the magnetic field, every now and then, kind of goes kablooey and ejects this solar wind, this solar flare, that then eventually gives rise to a wind of plasma that then hits the Earth's atmosphere and causes aurora. Anyway, believe it or not, there are physics similarities between this and this disruption in these laboratory plasmas. But there are some very new designs and new ideas by which we can control plasmas. And I'm going to show it here. Here is a plasma in red. this is a calculation, and the blue are magnets. And if you look at it, you can see it's a donut, but it's all crooked and shaped in an odd way. And if you looked at it, it looked like these magnets were, you might think they were nice circular magnets that were hit by a truck or something. But this is a very, very carefully designed magnetic field, designed by physicists because it makes a magnetic field that is invulnerable to these disruptions. So I'm just giving you an example. These are what I might call the 21st century design. It's based upon some physics insights from about 20 years ago, but this could not have been designed 20 years ago because you needed modern computers to convert these new physics ideas to a realistic design. This is a design that is under construction in Germany, and they'll be testing this in a few years. So where are we going in fusion? One difficulty in developing fusion is to develop it isn't cheap, because you have to build bigger and bigger experiments as you get closer to a reactor to understand what's going on. So there's a next very big step coming up that you'll be reading about, an international step in fusion. And it's called ITER, and let me just give you the physics motivations. All plasmas that have ever been produced to date in all the experiments around the world are heated by the experimenter. We drive a current through it. So it's like we're making a fire, but we're keeping a match under it to keep it hot. And so if you go back to the schematic of the fusion reaction, you have the deuterium and tritium nucleus, they fuse and give rise to helium and a neutron. We're heating, we're providing heat that keep these nuclei hot and fast moving. If we turn off the heating that we're applying, the plasma cools down and goes away. So it's not self-sustaining in a way, like a fireplace should. So there's a next big step in the World Fusion Program to make a burning plasma. And this is going to be, we can take the match away, and it'll just burn as long as we keep fuel there, just like in your wood in your fireplace. We say that this is self-heated. And to give you an indicator of how it works, in a burning plasma where it's just self-heated, some of the fusion energy that's produced in these helium nuclei is redeposited back into the background plasma to keep it hot. So the fusion energy is produced. Some of the fusion energy escapes. Neutrons are neutral. They're not confined by the magnetic field. The neutrons escape, and their heat is converted to electricity. The helium nuclei are confined in the plasma, and their energy is then redeposited back into the plasma to keep it hot. It's a beautiful system. That's how it works. So it'll be self-heated. And this is going to be a big milestone, because the self-heating could alter the physics a bit. So this is going to be accomplished in a big international experiment, which is unprecedented in terms of the physics it'll do and also in terms of sociology. And first let me repeat the physics. This will produce a burning plasma. It's under construction now in the south of France. France is going to be the host. It will produce 500 megawatts of fusion power for about 500 seconds and longer. So this will really, I would say, demonstrate more the reality and feasibility of fusion power. It will produce 500 megawatts of power. I always have to figure that's about enough power to generate 500,000 homes, I think. I don't know the right worth of energy. And it will have a fusion power gain of 10. It will produce 10 times more fusion power out than is going into the plasma to keep it hot. So this will be a tremendous milestone for fusion. It's a large experiment. It's at the scale of a reactor, even perhaps bigger. Here's a person. And here you can make out the donut. It's a cutaway, so here's the donut. It's about twice as big as the tokamak I showed you the picture of with the man inside. So here's the donut. It's surrounded by these superconducting magnets, which are cooled to very low temperature, and superconductors have no resistance, so it doesn't consume any energy. All of this is put in a big cryostat because this is cold, like a big thermos bottle. So it's a big experiment, and it's an expensive experiment. And because it's big and expensive, it's an international partnership. And it actually was conceived, so to speak, politically in a summit conference between Reagan and Gorbachev. I don't know, got put into some political deal that gave rise to it. In the early 80s, it went through all sorts of design, also political up and downs. It involves the governments of half the world's population. This is half the world's population coming together to conceive, design, construct, and share the data taking of an experiment to generate energy for the world, to establish the science of generating energy in the world. The European Union is paying 45% of the bill, and for that honor, they get to be the host in France, and they get all the economic benefit of this thing, all the stimulus to their prestige and so on. And then the rest of us are 9% partners, and you can read down the list. It's sort of industrialized world. And I mentioned that fusion research is surging in China and Japan and South Korea. The construction is underway, and it's expected to be completed around 2020. It's unprecedented. There's no other science project has involved from conception the whole world coming together for a joint purpose like that. It's unprecedented in its managerial challenge. Imagine if you were trying to build a house, and and the plumbing was done by Koreans, foundation was laid by the Chinese, and so on, and they all have to communicate with each other, and the plumbing has to be compatible with the foundation, compatible with electricity, and so on. This is the challenge. It's an enormous cultural challenge. So I think the sociologists should have a ball with this thing. It's really interesting from that point of view. So it's a fantastic thing. And as I say, it's begun construction. The construction will be completed in 2020. So this is a view. This is the site. It used to be a nice green lush area. Now it's been destroyed, but it's for the greater good. There's a building to wind some of the magnets, headquarters building, open area, and this is an artist's conception when it's all together. So this is a very exciting project underway. Before I get to sort of when we're going to get fusion, I've been describing an approach to fusion where we confine the plasma in the magnetic field. And I want to indicate that there's a second approach that's completely different to generating fusion energy, different approach. And I want to show a few slides for that approach. And it's sometimes called inertial fusion energy or laser fusion. And in this case, it's almost the exact opposite of magnetic fusion. Magnetic fusion, we have a big plasma, and it's there, it's just held indefinitely. And a fusion reactor is there burning for months on end. In this other approach, you have a little tiny, tiny pellet, a little pellet of frozen fusion fuel, a deuterium-tritium ice pellet. And you zap it with powerful lasers, and it causes the pellet to get hot and undergo a little mini fusion explosion. And let me illustrate that a little bit here. And so here you have a little pellet, just imagine a pellet a few millimeters big. And it's made up of fusion fuel, and you hit it with lasers from all sides. The lasers heat the surface. When they heat the surface blows off in these orange arrows. So the surface blows off, and you get a rocket effect. Remember the rocket effect? The exhaust goes that way, or a balloon, and the rocket goes that way, right? That's the rocket effect. Well, here you have a rocket effect where material is blown off the surface, but then the pellet compresses. It compresses inward. It implodes by the rocket effect. The surface blows off. The fuel compresses by the rocket effects. As it compresses, it gets hotter and hotter and hotter. And you get fusion in a hot spot in the center, and then the fusion propagates out, and you get a little explosion. You have a little pellet that's exploding. It would, in a fusion reactor, that'll happen 10 times a second. Okay? So instead of holding the plasma steadily, you get 10 times per second, like an internal combustion engine. Okay? And that generates energy. This is a picture of a pellet, so it is small. The pellet, in the most popular approach, is put in a little can. Here's a little can, and the pellet is in the can. Can't see it because it's in a can. And then In a particular experiment, I'm going to show 192 lasers enter a hole in the can. Here's the pellet, and there's a hole on each side. The lasers go in, and what they do is they heat up the can, and the can emits X-rays. The X-rays, instead of the lasers directly, heat the surface, and the pellet implodes. It's called inertial fusion energy because the plasma that's produced when the pellet is turned into a plasma is not confined in any way. It just blows apart in a billionth of a second. It's only slowed down by its own inertia, so it's sometimes called inertial fusion energy. It's not a great title. This is a real experiment when it was being assembled. Inside this big spherical chamber with all these holes is that little millimeter-sized pellet. Okay? It's put in a huge chamber. You know, see how well you can detect what's going on inside. You have holes for lasers to go in. This is an experiment called the National Ignition Facility in Livermore, California. And and these are the lasers that bombard that little teeny tiny pellet. These are sort of a football field full of lasers. So it's the most powerful laser in the world by far, and experiments are underway. These experiments are funded for defense reasons, actually, because some of the physics and science of that little mini exploding pellet has similarities to nuclear weapons that I don't know about because it's all classified. I don't know about. But it has a secondary goal of fusion energy. So where are we going? Here's a U.S. roadmap for fusion energy. When I say a U.S. roadmap, I don't mean an official U.S. roadmap because this government has no roadmap for fusion energy. This is a roadmap which is kind of a scientific consensus. But here in the United States, here's our present moment. And I show pictures of 3 facilities. In the United States, there are 3 major fusion facilities. One is in a company that's funded by the Department of Energy, General Atomics in San Diego. This is the experiment here at Princeton, and CMOD is an experiment at MIT. So there are 3 major fusion facilities and a broadly distributed throughout universities and laboratories, a research program in how we can find these plasmas. This is the present day. And then we're also, I didn't put it here, we're also constructing ITER. So the US fusion program is $400 million a year. Around 2020, ITER will begin operation, and we will begin what I refer to as the ITER era. That ITER has to be accompanied, it will be accompanied by a research program to solve all the problems that won't be solved in ITER and to have a workforce that we can take advantage from the results from ITER. And this is a detail I won't get into. Most of us think we also need in the United States a facility that will produce fusion energy here as an experiment to study problems that are complementary to problems that will be studied in ITER. So here's sort of a 15-year period called the ITER era. And all this information then will be enough to allow us to build a full power plant. A full power plant, the first one that you build will be called a demonstration power plant. The first time you build it, it's a demonstration power plant. So here, you know, it's hooked up to the electrical grid and it's a full-blown thing. And it's hard to predict the future. But you know, this would be about 2035, and then the world enters the fusion era. And we really start the beginning of power generation by fusion. This kind of vision is shared by scientists all across the world. When Korean scientists get together and scratch their heads how to do it, everybody ends up kind of with a similar time scale, with a similar endpoint, with lots of variation in details. What's the best experiments to build along the way? But the broad outline, this is kind of I would say, a worldwide consensus. So I'm going to conclude and leave time for questions. Let me say a new field of physics has been developed, partly or in large part because of this fusion quest, although there are other reasons to do it, for example, as I say, astrophysical reasons. scientists are confident that we can make fusion power for large-scale use. I think there's no question that we can do it. The only question is how attractive it will be, how much it will cost, when it will occur. Those kinds of questions. Whether or not we can make large-scale energy by fusion, I think most of us would say the answer is surely yes. Fusion research across the world is absolutely surging. I mean, I'm sure there's a similar story in many areas of science that Asia is just really galloping ahead. China and South Korea entered the fusion program seriously maybe 15 years ago, something like that. And now, across the world, recently there have been about6 state-of-the-art facilities that have been built outside the United States. When they hit their stride, will be more scientifically powerful than anything we have in the United States. So, at the same time, I have to say the U.S. is a little bit faltering in its commitment to fusion. And you know, we're all in this ITER project, and the U.S. commitment to ITER is hanging by a thread. It's not clear that the U.S. government, there's actually a debate within the government whether it will fulfill its commitment to this international agreement to ITER. All other countries right now are rock solid. Japan had a tsunami and an earthquake, and in that same year they've tripled their contribution to ITER, their financial contribution to ITER, because that's what's needed. The European Union has these well-publicized economic problems, and over the next 2 years they'll be contributing over $2 billion to ITER in those 2 years alone during this economic crisis. The United States is supposed to, in 2013, to meet its ITER commitment, contribute about $200 million, and it's not doing it. So it's embarrassing. If there's a societal will, we can surely have this clean, safe, abundant domestic energy source in a lifetime. How much will it cost? It's expensive. What will it cost? Well, the rough annual cost, if we had a very aggressive fusion program that would really get there as fast as reasonable, it would require about 0.1% of the annual U.S. expenditure on energy. We spend each year about $1.5 trillion on energy in the United States. And if you really wanted a full blast fusion program, it would be something like $1.5 billion a year, which is about 3 to 4 times bigger than it is at present. So for every $1,000 we spend on energy, you take one out and put it to the fusion program, that would be a super aggressive program. So if there is a will, we think there's a way. And thanks for your attention. So I'm to answer questions. Yes, sir.
Who's going to control the patents on these things, and how much savings would it be to the consumer when it's all up and running?
Who's going to control the patents? To date, you know, people patent things here and there, but it's such a big science program that all the science has been shared. So it's not really, it's up to now, there's been no problem. It's been a scientific thing, all open. As you get closer and closer to a reactor, and there are some further, less scientific, more technological inventions, then there will be patents on little bits and pieces, but no one can patent the big ideas. That will be available to everyone. The data from ITER will be available to all partners. If the U.S. drops out of ITER, it will be a problem, but it'll be available to all partners. When does a consumer benefit? I mean, the consumer will benefit when fusion is generating energy because it won't contribute to global climate change, and it'll be available to everyone. The best engineering projections predict that it will be cost competitive. So I mean, it's not a money saver. We're not doing this to save money. We're doing it so that we can power an economy in a clean, limitless way. So that's where we'll gain. And it's projected to be economically competitive, but it's pretty hard to predict economics 30 years from now. Yes, sir.
In 20 words or less, how the heck do you measure these fantastic temperatures?
A very good question. You can't put a thermometer in. Don't try it. The way we do it is, the most reliable way is you take a laser. You shoot the laser into the plasma. Okay? The laser interacts with the moving particles in the plasma and gets scattered and leaves the plasma. You measure the scattered laser light, and you analyze that, and you can infer how fast the particles were moving that did the scattering of the laser. And that's how we measure the temperature of part of the plasma. Another way is the plasma generates light because the atoms in the plasma that are generating light, just like in a neon tube. You can measure the characteristics of that light and infer what the temperature is. All kinds of remote ways like that. Yes, sir?
So to get this energy out, you have to put energy in.
Yes.
And as I recall, the last I heard about fusion was that it took more energy in than you're getting energy out at this point.
That's right.
So what is that cross?
Right. So in the biggest fusion experiment, where 15 or 16 million watts of energy was generated for a second, 16 million watts was generated, but something like 20-25 went in to heat it. So you got 70% of it out. In ITER, you get 10 times out. 10 megawatts, 50 megawatts will be used to heat the plasma. 500 will come out. That'll happen in ITER. You get more energy out than in. Yes, sir?
Could you say a few words about some of the anticipated engineering problems associated with extracting energy?
Yes. Problems I didn't discuss at all today are the problems of surrounding this thing with a material. And there are two aspects to that problem. The heat that comes out of a fusion reactor will be 1/10 of the heat flux that you get on the surface of the sun. Or it's like having 100,000 light bulbs spread over an area about this size, a lot of heat. So you have to develop materials that can withstand that. That's number one, material science and technology problems, to develop materials that can survive that kind of heat flux. And there are ideas and research in that. The second thing is that you then have to surround it by what I might call a smart material structure. It takes the neutrons that comes out. I didn't get into this, but the neutrons in the surrounding structure is used to breed tritium. And then the neutron, you have to take that heat and you have to take the neutron energy and convert it to usable heat. So that gets into the whole area of having materials that can withstand the neutron flux. And then it involves, how you have a flowing substance that takes the neutron heat and takes it out of the reactor. Those are some big material science-related technology problems. Those are the biggest ones. Yes, sir?
Notice that the final ITER design that you showed did not seem to reflect the complexity of that German machine.
Yeah.
How are you going to get the design capabilities of the German machine?
Yes, good question. It's a good question. So the most advanced concept is this tokamak, which is not that crooked design. And since that's the most advanced, we're using that to take us to the stage of this burning plasma experiment. The newer designs are not ready to do that yet. So you have a mainline concept that's taking us to burning plasma, and then right behind it you have another concept that might be better, but is less well developed. So in developing any technology, you'll have this kind of thing, and how much resources you put into maybe the smarter one that's not as highly developed versus the slightly dumber one, it's not a good term, that's more highly developed. And so for the next big ITER step, we're going to do the tokamak. In the meantime, the world is looking at this other option, and and then we'll see whether the other option is working out well enough to do a leapfrog ahead of the tokamak. So it's yes, ma'am.
I have two questions.
Yeah.
First of all, why do your experiments run for such short periods of time? And the other one is, what are those electromagnets made out of, and how hot do they get?
Okay, so that's I'm glad you asked both of the questions. In the United States, all the experiments, those 3 experiments, last for 1 to 5 seconds or 10 seconds. And the reason is that the magnets only run that long, just a hardware reason. We have a magnet that makes a magnetic field, and the magnet only has enough power in the power supply to run for a few seconds. It's just a technological limitation of the magnets that are being used. These electromagnets you just asked about. So the electromagnets have to be cooled. So, you know, they carry in current, and current will heat up the magnets, so the magnets are actively cooled. Now, the rest of the world, with these new facilities, have entered the superconducting magnet era for fusion. And they use magnets where the magnets are cooled down to almost 0 degrees Kelvin. They're cooled down, and they're superconductors. And because they don't consume any electricity, they run for long periods of time. So the rest of the world has entered what we call the steady state era of plasma experiments. So it's been, for the most part, just a technological limitation of the magnets, which the rest of the world now has gotten beyond, but the US hasn't made the investment for that. Over here, Douglas.
Does the old concept of the stellarator still have any life left?
Well, these, so in this laboratory, the Princeton Plasma Physics Laboratory was founded in 1951 by Lyman Spitzer, who was a great astrophysicist, and he also got interested in this problem. And he came up with a design that wasn't a tokamak, it was kind of a complicated design called the stellarator. Okay, it didn't work. Okay. But over the decades, that kind of concept has been transformed into the new design that I just showed. So in the trade, we call that a stellarator. But it's completely different than the one that was invented by Lyman Spitzer a long time ago. So yeah, it's still alive and well, but in new incarnation. Yes?
One of the reaction brought up is doubly charged helium. So what happens to it? I mean, how does it get to be like normal helium, and what is it?
Yeah, so the helium is doubly charged helium, and when it's born, it has a lot of energy, and it gets trapped in the magnetic field and stays in the plasma. And slowly it transfers energy to the background plasma, and then eventually it makes its way out of the plasma and just gets deposited on the wall. So eventually it just accumulates on your wall harmlessly, not a problem. Yes?
I'm concerned about potentially very high materials costs. The materials of the tokamak or whatever are going to have to be replaced at some point because they're not going to last forever. And it's going to be fantastically expensive. Is it going to be like a small-scale version of decommissioning a nuclear reactor to take out all this radioactive stuff and then put it all back in again? Can you talk about that?
Yeah, that's a good question. So that's right. So this goes back to the question about the technological challenge. So you have the plasma surrounded by a material. Okay. And if the material, and the plasma hits the material and causes it to erode, and the material can only last so long, it's got to be replaced. If you have to replace it every 6 months, too expensive. Yes, you're right, because to replace that, you got to take this thing apart. That's a big, temporary decommissioning. If you have to replace it every 5 years, it's economically competitive. So you have to have materials that can survive long enough that you get high enough availability of the reactor that it's economically competitive. This is a critical question you raised. It's not yet a solved problem, and it's an area of research to develop these materials. Yes, sir?
What do you envision the transmission grid? Few sites as opposed to many power plants. They'd be producing presumably a huge amount of electricity.
Yes.
That has to be
Yes.
transmitted.
In that sense, this is conventional, so it can actually hook right into the existing transmission grid. It's just like we have big centralized coal-fired plants, big centralized nuclear power plants of today, and this will be just the same. It's the same thing. You have some big thing that generates heat that's converted by turbines to electricity. And so it doesn't pose any extra problems. But it's big centralized. You're not going to put fusion reactors on your roof. Okay? It has to be big. If it's too small, you're going to lose the energy too quickly. So it doesn't present extra challenges in that regard.
Is it really that kind of expansion at one site as opposed to multiple sites that we have?
You would have multiple sites like we have now. I mean, a fusion reactor is envisioned to be 1, 2 gigawatt reactor, just like so
That would be one national.
No, it would not be one national reactor. Gigawatts, yes, sir.
How big realistically would it be if you saw some of those pictures of the very laboratory scale compared to a human being. And so, for example, with your the demonstration size, third generation out, how big would it be?
It would be, you know, we think it will be, I showed you that picture of ITER,
Right.
okay? And so that we think would, depending on how the physics goes, a reactor could be a bit smaller than that. But it'll be that scale. It's not going to be 3 times big. It'll be that scale or maybe a little bit more compact. So they'll be big things, but not too big. Yes, ma'am.
Can you talk about the political scenario here? Are the people actively opposed to this, or is there indifference? What's the politics on
Well, it's an interesting thing, boy. It varies year by year, and it varies place to place. And I'll say at the beginning, I don't see a particular correlation Republican to Democrat, so it's not in that. We're not talking about that kind of politics. But in the last administration, at the Department of Energy, there was a person in charge of science that was very, very, very strongly for fusion, and he brought us into ITER and wanted us to fulfill our commitment to ITER and at the same time strengthen our domestic program. It was all great. Nowadays, in the Department of Energy, they're looking very short term. It's sort of amazing. And they constructed an energy policy, a strategy rather, that looks forward about 10 years. And it's all about things we should be doing. It's all about, you know, more efficient batteries, more energy efficient buildings, electrifying the car fleet, all that kind of thing, looking forward 5 to 10 years. And they're not focused on the longer term. In my opinion, the world doesn't end in 30 years. They're not focused on the longer term in the Department of Energy at this current moment. At this current moment, I find that in Congress there's strong receptivity toward fusion. I find that. 20 years ago, you'd go to Congress and they were very cynical about fusion. So it kind of oscillates. The thing is, in this government, in the administration, the way it works, you have to get the Department of Energy, the Office of Management and Budget, and the President's Science Advisor Office all on board. Then you go to Congress, you got to get the House and the Senate on board. So you got all these players have to line up together, and it's really hard to get everybody agreeable at the same time. And that's why I almost worry that it's structurally difficult in the United States and our system to get a commitment to solve a really long-term problem. Yes, sir.
High pressures, high temperatures, exotic materials. How do you handle the safety aspects?
The high temperature, you know, you have this 100 million degree thing in the center, but the wall that surrounds it, it will be at about 500 to 1,000 degrees. So you don't have to deal with anything, any material object that's at 1 million degrees. That's all in this gas. Okay, so it's 300 million degrees in the center. When you get to the wall, you know, the plasma is something like 100,000 degrees, which is getting pretty cold. But that's the plasma. You know, the wall that surrounds it is just 500 to 1,000 degrees. Okay, so you're dealing with ordinary kinds of temperatures, so that can be handled safely.
What about your pressure?
The pressure, even though it's 100 million degrees, it's very dilute. So it's not. There's no explosive pressure. It's maybe, you know, the air in this room is in an atmosphere, and in a fusion reactor, I forget, it's something like a few atmospheres. It's nothing. It's easily contained in the vacuum chamber. Why is that? Because this 100 million degree plasma will be about 1 million times more dilute than the air in this room. It's very dilute. Okay? There are billions and billions and billions of particles, but it's dilute compared to the air in this room. So it's much hotter, but it's much more dilute. Yes.
You talked about how the United States is lagging behind many other countries around the world. My question relates to the potential brain drain that the city might be getting into. Do you have trouble recruiting the best and the brightest for what you're doing now, or are they going elsewhere?
We don't have trouble, but we're at a turning point. We have a scientific workforce in fusion that's second to none in the country, but we're right at the precipice of maybe dismantling it a little bit. So right now, we get the best and the brightest in this country, absolutely no problem. But the newest facilities have been built overseas. And so there is a very serious danger of the center of gravity shifting overseas and that kind of brain drain occurring, most definitely. And it takes about 20 years to build up a scientific workforce. That's an observation. Because I had mentioned that about 15 years ago, China and South Korea started really surging in fusion. They built these great facilities, better than what we have here, but they can't run them so well because they don't have the scientific workforce. So they look to the US and the European Union to go over to China and Korea and work with them on their experiments. Now, in 5 to 8 years, they'll be up to speed. But it takes about 20 years to build a scientific workforce. That's why it's so important that we keep ours healthy here. Yes?
The cold fusion,
Yes?
I'm assuming that's the popular name for the alternative that shows up in the press periodically.
Yes.
Is that actively being looked at by you folks and the MIT folks as well? And is it a viable alternative in your mind yet?
No, cold fusion, this happens in fusion. Cold fusion, if you remember, whatever it was, 20 years ago, I can't remember now, University of Utah was claiming that just room temperature, little setup, tabletop, that they were getting fusion reactions generating heat. It's not true. It's not true. It hasn't been shown to be true.
Inertial fusion?
No, inertial fusion is legitimate. It's totally different. This is a totally different thing. So it's very unfortunate that that's not true. It's not fusion. Hasn't been shown to be fusion. And to this day, hasn't been shown to be fusion. If they show it tomorrow, that'd be great. But it hasn't been shown to be fusion. And it's sometimes referred to as pathological science because for lots of reasons, so a couple of chemists got together and they kept everything secret. They didn't publish, they didn't present, and then they went to a big press release. And it was all done wrong. All done wrong.
But is inertial fusion a viable alternative?
Yes, inertial
fusion. Are you
fusion.
actively looking at it?
Who's you? Me? Yes. Yes. Yeah, the answer is yes. The answer is yes. Now, Princeton, MIT, the focus of our work is magnetic fusion, but we do a small amount of work in inertial fusion, but that's our specialty. But yes, that's a totally legitimate, exciting approach, complementary to the magnetic approach. Absolutely yes. Yes. Not to be confused with cold fusion. Yes.
Is this related in any way to CERN?
No. So CERN is a different part of physics. And so CERN is the Center for European Nuclear Research in Europe. And that's where they have a Large Hadron Collider you'll read about. So there's another field of science called elementary particle physics, where you're trying to understand what makes up the smallest bits of matter. Very fundamental topic in physics. So they build these big donut-shaped things, these big accelerators that cost billions of dollars, and they smash particles together to see what comes out to understand the fundamental forces and particles of nature. And that's particle physics, sometimes called high-energy physics, because you need to get these particles moving at high energy. And that's what's studied at CERN. So what it has in common is physics, and they're big donut-shaped things, and it has lots of money. It was a different purpose. Yes?
Hey, I'm really curious. You talked about the scope of 100 million versus 10 million degrees.
Yeah.
Why not start with the sun at 10 instead of going right to the 100? And then when you talk about those disruptions coming, you're going from 10 million degrees to 0 in less than a second. How does that happen?
So I'll answer both your questions. The sun can do it at 10 million. The sun can generate all this energy at only 10 million degrees because it's so dense. It's so dense that even at 10 million degrees, you get enough fusion reactions to generate a lot of power. But in the plasmas we have, because we can't get anything so dense, we really have to get it hotter so we get more fusion reactions with a more dilute gas than the sun is. So if we just do it at 10 million degrees, the number of fusion reactions is going to be too low to generate a lot of energy. If we take the gas we had and make it a million times more dense, we can't do it physics-wise, hard to do, then we can do it at 10 million degrees. What was the second question?
Oh, about how do you recover these disruptions? You're going from 10 million degrees to 0.
It happens because the magnetic field is like I use the analogy that I've used. The magnetic field is like a track for the particles to move along. So you want the magnetic field to be nice, nice smooth pattern, and every once in a while that track, as we say, goes kablooey. Okay, and it breaks up. It breaks up, and it tears up. So the magnetic field gets all wiggly, and then the particles get thrown out of the machine. Why does it get all wiggly? Okay, and it gets wiggly because it's kind of like a tire blowing out. Okay, so you put too much pressure in a tire, and it'll just blow out. And that's what's happening. There's a lot of energy in these plasmas. We call it free energy. There's a lot of free energy that can give rise to what we call instabilities that can get all crooked. So it's a big topic you just asked about.
Well, thanks.